All right, good morning, everyone. So we're going to talk about how to implement these neural networks in PyTorch today. So basically there's a recipe. It has a number of steps, but we can learn how to do each one of them, and it's not too bad. So the first thing we need to do is we need to construct, basically put our data into a framework that PyTorch can deal with. Then we construct our neural network from all the little pieces. Then we select our optimizer and our loss. And then we run a training loop, a for loop that, as we'll see, calls the optimizer, computes gradient using backpropagation. And then once it's trained, we can apply it on new data. So we're going to go through the code that generated that experiment we saw at the beginning of this unit, where we had two-dimensional data and there was some green points in the middle and blue points around the outside, and we wanted to construct a two-stage network that had 4 hidden nodes that made 4 linear classifiers, and then the second stage basically classified the outputs of the first stage. Okay, so first step is to construct the dataset and data loader objects. So as you see, the very first thing we do, we need to import the torch. That's like basically the PyTorch library. And then we have to import these utilities that deal with data. And the first thing to notice is that when we work with PyTorch, we have to use a different data type. And this is called a torch tensor. And so this will take our NumPy array X, and it will convert it to the kind of, it's a very similar object to a NumPy ND array, but it's PyTorch's version. And so that's the very first thing we do, and you can see we're going to do that to our features and our targets in our data set. So once we have the features and target quantities, then we create this, what we're going to call a data set. We put it through this tensor dataset command here. We give it our training data. And now that we have the data set in the form that PyTorch wants it, we can construct what's called the data loader. We give the data set to the data loader. And the data loader is going to be in charge. One of the main things it does is it pulls batches out of the data and feeds us random batches when we ask for them. So here we're going to tell it the batch size. The data loader is also good in dealing with if you have multiple GPUs, or if you somehow need to spread the computation over multiple units, the data loader is good in dealing with that. So we create this loader object. And later on, we'll see that this is how we're going to call that loader. So this is going to be within our for loop. We're going to say enumerate loader. That's going to output data. If you remember, this kind of for loop is one where the batch is going to be a variable that indexes like 0, 1, 2, 3, and so on. And then every time we go through the for loop, data is basically this enumerate loader. It's gonna ask the loader to generate a new quantity data. Data ends up being a tuple, combination of an X batch and a Y batch, and this is what we're going to give to our training algorithm. Okay, so those are the main things. We have torch tensors, data set, data loader, and that's so that we can draw mini batches later. All right, any questions? Okay, next step is constructing the network. So for this, we're going to import the neural network library from PyTorch, which is going to give us a bunch of other capabilities. And so here we're just setting the number of hidden units as 4. We're going to use that later on. But the main thing we're doing here is we're constructing this neural network using a class. And a class, we talked about this before, this is like object-oriented concept where you always have an initialization routine that is called when you instantiate the class, and then you have several other things, functions and so on. So in this particular class, we have a forward function that implements a forward pass through the network. The other thing that we do when we initialize it is we set up our, so these are these kind of variables that are going to be known within this class. And these things in particular are the different parts that we're using to construct our network. So we're going to construct an activation function. In this, we're going to use sigmoid. So the sigmoid is one of the activations in the neural network library. And then we're going to have these two linear layers. We're going to call them dense, just because we'll see in the next unit when we talk about convolutional neural networks, there's another way to make these linear layers that have a slightly different structure. In any case, we're going to call the neural network linear library, and here we're going to have to tell it the dimensions, so the number of inputs and the number of outputs. The number of outputs for the first layer is going to be the number of hidden nodes, NH. And the second of our linear layers, it's going to take in NH and put out an out. And this activation is something we can use several times, as we'll see. So now we've constructed all the different pieces of our network. And when we call the forward function, this is going to take in an input X to the network. And as you can see, it's going to put X through that dense one layer. And then the output of that is going to be put through the activation layer. And we're just going to overwrite X again so that we don't have to create any new memory. And then that is going to go through our second dense layer and our second activation to give us the output. So that's going to be one of the functions within our network. And then finally, we're going to instantiate our network by telling the network what the dimensions are. So we want NX inputs, NH, hidden nodes, and one output. And so once this model is constructed, you could do like model dot forward, and then you could implement this forward pass. All right, any questions on the network? Okay. Third step, we're going to select the optimizer and the loss. So for this, we import the optim library. And so there's going to be many options available to us in terms of this optimizer. So we talked about stochastic gradient descent in our class. That's kind of the most simple version. There's a lot of variants of stochastic gradient descent that have other improvements, like ways of changing the step size, or something called momentum, which kind of keeps the trajectory going in a direction with a bit of momentum. And these are a number of the ones that are implemented in PyTorch. The one that is the most famous nowadays is Atom. That's the one that everyone seems to use as a default. So we're going to use Atom ourselves. We're going to select that as our optimizer. We also have to tell the optimizer what parameters it's going to be optimizing. So this model.parameters will tell it all the parameters of all these, of all these guys here. We also have to tell it the learning rate or step size. We're just going to tell it to use 0.01. So that's our optimizer. Now that's set up. And then the other thing we have to do is define our loss function. So we're going to use this binary cross entropy loss because we have a binary classification problem. We'll talk about some other options in a few slides. So we'll call this criterion. There's other parameters that you can specify for these optimization algorithms. Some of them are specific to the algorithm. Let's see. And yeah, so other options for the loss, like if we had a classification problem with more than 2 classes, we would use cross-entropy loss. Or if we were doing a regression problem, we could use MSE loss, which will essentially implement RSS. Or if you wanted to penalize some of the absolute values, you could do L1 loss. Also, once you create these losses, you can easily scale them and combine them. For example, you could do MSE loss plus some parameter lambda times L1 loss if you wanted to implement something like lasso. So it's pretty capable what you can do with these losses. All right, and if you want to know more about some of these other algorithms, I put some links here. All right. We won't get into the details though. Okay, so now everything is set up. We're ready to do our training. So this is where we have a for loop, or actually two nested for loops. The outer loop is going to be indexing over our epochs. Remember, an epoch is when we make a full pass through all of our training samples. And then the inner loop is going to be over each batch, or mini batch, and that's just, a small piece of our overall training data. And when we go through this loop, we want to not only update our parameters, but we also want to keep a record of what happened, like the loss and maybe the accuracy as well, so that we can later on plot what happened over the iterations to see if we're making progress, because we need to set things like the total number of iterations and so on, and we want to make sure that things are indeed working and all that. So first of all, we're going to declare the number of epochs to be 2,000. We're going to define a print interval, which will, every 100 epochs will print out a report of the loss and the accuracy. And we're also going to instantiate some vectors of zeros that will eventually hold our loss and our accuracy per epoch. So these are going to be vectors of size epochs. All right, so in the outer loop, the first thing we do is we're going to reset our error counter at 0, reset, the total is going to count the total number of samples that we've seen, and then the error is the number of errored samples, and then the ratio will be the error rate. And we'll also have an empty array that will grow to contain all the losses in the batch. And then once we go to the next epoch, we'll reset it as empty again. Okay, so now we have our inner loop over our mini batches. And as we saw before, this is where we call the data loader and we pull out our latest mini batch, which we'll call data. And then we expand data into the X batch and Y batch, so basically the features and the labels. Now one thing, so PyTorch is a little picky with how everything has to be. And one thing that's important is that both of these guys have to be, in this case, we want them both to be matrices. And it turns out that X batch is a matrix, but Y batch is just a vector. It only has dimension 1. And if we don't correct this, we're going to get an error later. So the first thing we do is we change it with this view -1,1. This resizes Y batch to a quantity of batch size, 1. Okay, so now, instead of thinking about it as a vector, you can think about it as a matrix with 1 column, which, when we write things down on paper is the same thing as a vector, but in terms of how PyTorch or NumPy handles it, it started out to be a 1-dimensional quantity, and now it's a 2-dimensional quantity. once we're done. So that's an important little step. Okay, and so now what we can do is we can put that X batch through our model to get our output. And now that we have the output defined, we can compute our loss. So remember, we established criterion, that's our loss function. We're going to give it the output, which is going to be the predicted samples, and Y batch is going to be, sorry, these are not predicted samples, these are the output activations, so they're numbers between 0 and 1. And we're going to give it, let's see. Yeah, and then these are the true targets. And from here, it can compute the loss. And then we're going to append that loss to, let's see, we're going to extract the loss from here, and we're going to append it to this empty array. So this is going to be growing. Every batch is going to have a new entry. So within that epoch, we can see the different losses over the batch. All right, so now we're going to finally compute our gradients using backpropagation. And so for this, the first thing we do is we zero the gradient in our optimizer, because otherwise it stays at what it was. And then we do this loss dot backwards. And this is going to do all that backpropagation stuff that we talked about in the last lecture. It's going to push the data backwards, compute all the different gradients, and store the result. And so like the optimizer and the loss, they are all talking to each other. So then when we do opt.step, it knows to get the gradient from the loss and to use that gradient when it does its optimization step. And so now finally, so that's optimization step is done. And we can finally quantify how well we're doing in terms of accuracy. So we're going to, or error rate. So we're going to take our output, which is, if you remember, that's a number between 0 and 1. We're going to round it, which is going to make it either 0 or 1. And that's going to be our guess, our Y hat. And then we can look at the difference between the guess and the truth. And so these quantities are both going to be 0 or 1. So their differences are going to be either 1, 0, or minus 1. When we take the absolute value, we're going to get 0 if it's correct, or 1 if it's an error. And so we're just going to sum those guys over the batch to get one number, which is the total number of errors in the batch. And then here, this is just the length of the batch. So we're going to add that to total. Now the reason we're doing this is because if the number of samples is not, number of samples within the data set is not evenly divisible by the batch size, the very last batch will have a different number of samples than the rest of the batches, have a little bit fewer. And so the length of the batch should be, what did we say it was? Was it 100? I can't remember how we said it. It was like 100 for all the batches are 100 except maybe the last one. And whether that's 100 or not depends on how many total samples there are in the data set. So that's why we can't count on the batch size always being the same. So that's why we do this. So finally, error is going to be the total number of errors within that batch over the total number of items in the batch. And then, let's see, so basically we loop over this. And so every time we go through our batch, we keep adding to our errors and adding to our total. And let's see. Right, and then still within here, we're going to look at 1 minus error over total. That's the accuracy. Multiply it by 100 so that it's between 0 and 100. And then we're going to take this accuracy and we're going to store it as the accuracy for that epoch. And remember, we have this batch loss that we've been growing over the epoch. We're going to take the mean over the epoch and we're going to store that in the average loss for the epoch. And so now for that epoch, we have the average loss as well as the accuracy. And we start over again. We clear out the error and totals. We clear out the batch loss. And we go through this over and over and so on. So that's the overall approach. As you can see, there's a few steps, but it's relatively straightforward. And this is just, once you see this done once, then you can replicate it yourself for other problems. It's more or less the same. All right, any questions on this loop? Okay. All right, so then the last step, let's look at some plots here. So this is the loss versus our epochs. And you can see it comes down very quickly and then eventually it kind of settles out and is smoothly going down, and probably would have made a bit more progress if we would have let it run a little bit longer. But it looks like it's mostly done converging. And then our training accuracy, you can see it takes a big jump. And then it kind of doesn't do much over this region. I mean, things are getting better in terms of our loss, but we don't yet see it manifest in terms of the accuracy. But then at a certain point, all of a sudden the accuracy starts increasing. And then in this range here, it sort of settles out, and it looks like it's going down and up a little bit. So that's the performance we see. And if we do this experiment again, it's going to use a different random initialization every time, and these curves are going to look a little different every time because of that initialization. Oh, also there's randomness in the mini batches too. It's another source of randomness. Okay, so finally we're ready to create this plot. And okay, so to make this plot, once the network is trained, we essentially need to make a very fine grid of all these points here and feed each one of those points is a pair of x0, x1. Want to feed that to the network, push it through the forward pass, and the network is going to give out this A output quantity, which is a number between 0 and 1, and that's essentially what we're plotting here using this red color map. Okay, so to do that, we first are going to say, what are the extents of our x0 and x1? So those are the x min and x max. I guess here, x min and x max. And we're going to use something called mesh grid that you may have also seen in MATLAB to create this grid of all of these points in 2 dimensions. So first we're going to say, okay, 100 points per dimension. That's how finely we're going to sample. And now we're going to make a vector of the x0 values for all these points. So we're actually, this is just the x0 values, so just going from here to here. So it's lin space from x min to x max. Those are the extents and then number of points in the plot. So we're going to do that for x0. We're going to do it for x1 as well. And finally, here's where we use mesh grid. So mesh grid takes in this vector samples, and then it returns 2 matrices. One of the matrices are the x0 points for all of these, and then the other matrix is the x1 points for all of those points. So those are these matrices here. And now we're going to take those 2 matrices, we're going to turn them into vectors using Ravel. And Then, so this is going to be a list of all the x0 values for all these points, and this is a list of all the x1 values. And you can see we stack them next to each other. And so we're going to create a matrix that's, let's see, it's going to be, so there's 100 in each dimension. So there's going to be 10,000 points total. And we're going to have, so there's going to be 10,000 rows and 2 columns in this matrix. So we can think about this as like a new feature matrix that we're just using for the plot itself. All the different samples in this feature matrix are just the different samples for our plot. So this has been all done in NumPy. So the final thing we have to do to use it with PyTorch is we have to convert it to a torch tensor. So then we're finally ready. And now putting it through our model is very easy. Just model xplot tensor does the forward pass. And this gives us a sorry, let's see. Yeah, so this is going to give us the A0 output. So there's a little, this should say AO plot. I changed this in the most recent notes, but I forgot to upload them to my iPad. Okay, so this is, these are the A0 quantities that we're going to be plotting. And this is going to be formatted also as a torch tensor. Now to use that in NumPy, we have to format it back in NumPy. So how we do that is you do .detach.numpy. So this converts it back to NumPy. So this is now a NumPy variable. And this is going to be a long vector, 10,000 values of all the A0s sampled there. So we're going to reshape that into a matrix of nplot by nplot. And this matrix version is something we can plot using imshow. This is like an image plotting command. We can think of this matrix now as an image. So one small detail is that when we usually plot images, we start 0 at the top and go down. And here we're starting 0 at the bottom and going up. So we have to do this flip UD. It flips the this matrix over on along the rows. And we also have to tell imshow a few things about the limits. So we tell it that. It plots this, and then we also want to know what the colors mean. So with color bar, it plots our color bar. So that's essentially how we can call the network to plot all these. And then now we overlay the blue and the green samples. And this is just using the original training matrix X. Yeah, and we create these index sets. So I0 are all the sample indices where y equals 0, and then I1 is all the sample indices where I equals 1. And that way, if we restrict X to sample indices I0, we can get all the blue dots, or I1 gives us all the green dots. All right, so that's essentially how we plotted this. All right. Any questions on this? Okay, great. And we can also visualize the quantities in the hidden layer. So let's see how to do that. So remember we have our xplot tensor that we created. So we can put that through the individual stages in our model. We can put it through model dense 1. And that has our trained weights in it now. And then we put it through model.activation, and we know that this gives us our hidden activations. So these are PyTorch tensors, so we need to convert them back to NumPy in order to plot them. And then that's a long vector. So if we want to convert these into matrices, we need to reshape. And actually, we'll talk more about this, but this is known as a tensor. This is a matrix, you could say, with 3 different dimensions. So it's nplot by nplot by nh. So this is like when nh, or when the last index is 0, you get this matrix. When the last index is 1, you get this matrix, and so on. So this is like a stack of 4 different matrices all together, which we call a tensor. All right, so that's how we plotted these. Well, let's see, I guess, is that where we plotted it? That's how we created it, and I think down here is how we plotted it. Oh no, actually, this is the range. Yeah, sorry, we plot it in this for loop. We plot one at a time. The other thing we're doing is we're extracting the weights, the trained weights. So we can do this using this command, state dictionary. So when you do model state dictionary, it pulls out all the different parameters into here, and then you can extract the individual ones. Like if we want the dense 2-layer weights, we can return those, and this is going to give us not only the weights but also the intercepts, or sometimes they're called the biases. Yes, actually, yeah. So this is where we get the weights, and then this is where we get the biases. So this is how we extract the weights. And finally, yeah, the rest of the stuff is for plotting. So we're going to go through the number of hidden nodes from one to the next, and so on. We make a subplot. We, again, plot the ith. You could say frame maybe within that tensor. Flip it, use imshow like before. If you want to get rid of these little ticks, you can do that here, and so on. All right, so that's how we did that, and yeah, so that concludes this demo. Are there any questions? Yeah.
Is there a saving method such that, say you need to run this after you close this, you can access it on, I don't know, like a workspace or something like that?
Yeah, there's a couple different ways to save data. So one way is you save things using the state dictionary, and then you can load them back in later. So then you could just save these variables. There's another way to do it using what's called the trace that I'll explain when we come to the project. I'll show you some demo code. And the nice thing about that method is it's more robust across different platforms. So like if you're on Windows and you save it that way, and then I'm on a Mac, I can load it and it will work. Whereas if sometimes with these other methods, it doesn't work across platforms. So that trace method is another way to do it. And yeah, we'll see an example of that with when we get to the project. All right, any other questions? Okay, so then there's a second demo where we apply a very similar network. Actually, it's the same network, but we're just going to change the number of input and output and hidden nodes. So we can use a lot of the same code, but we're gonna apply this to MNIST now. So for MNIST, if you remember, there are 10 classes. So that means we need 10 output nodes, one per class. We're still going to have the inputs are going to be an MNIST image is the input. And so you're going to essentially unravel that into one vector. And if I'm remembering right, is it 384 pixels in an MNIST image? It's some number of pixels that's basically the number of features that go into this network. And we're also going to use 100 hidden nodes. This is something that you can play with. Maybe you can get it to work a little bit better, but it works pretty well with 100, so we're just going to use that. We're going to use cross-entropy loss because we have a classification problem with more than 2 classes. For the hidden nodes, we're still going to use sigmoids. although you could try other things like ReLUs or TANH. We're going to use the Atom optimizer again with this learning rate, 10e minus 3, a little smaller than before. And in this case, we have 50,000 training samples and 10,000 test samples. So what we're going to do is we're going to just, we're not going to do k-fold cross-validation. We're going to do the simpler cross-validation where we have a training set, a test set. We'll train our network on the training set, and then we will apply it to the test set. And that way we can plot both accuracies. And actually every epoch, we're going to take our trained weights, apply it to the test set, and that way we can get plots versus epoch of the training and test accuracy. So the training accuracy, you can see increases and looks like it's converging to 100. And actually it's quite common in a neural network to get 100% training because you can make these networks very complicated. They can essentially memorize the training data set perfectly once they have enough parameters. But that does not mean that the test accuracy is going to be perfect. So as you can see here, the test accuracy is settling out at around 97%. But 97%, if you remember, is pretty good. That's also what we got with the SVM with a radial basis function kernel. So that's way better than logistic regression. And in fact, one of the advantages of this neural network compared to the SVM is that the SVM takes a lot of time to run even at what we call inference or test time, right? Because what the SVM has to do is it computes all those support vectors. And then if you just want to classify one test sample, you essentially have to do an inner product with all of your support vectors, or you have to do a kernel evaluation with all your support vectors. And so if you have a lot of support vectors, that takes a lot of time. This neural network, you just push this through and you do a few multiplies and sigmoids and you're done. So it's actually much faster to run. Also, 97% is probably not the limit. If we tuned things carefully, we could probably increase this a bit. So the point is, these neural networks are pretty powerful and pretty general. And it does take a little bit of time to train them, but they're very fast for inference, very fast at test time. So there's another demo here that you can also take a look at. All right, any questions on anything here? All right, so just a few more comments. So when we implement these two-layer neural networks, we do have to make some decisions. So one important thing is how many hidden units will we use? What type of hidden layer activation function should we use? With regard to the optimizer, we have some decisions to make. First of all, which optimizer are we using? What is the learning rate we're going to use? Another approach is to actually change or schedule that learning rate over the epochs. Typically, people tend to start at a higher learning rate and decrease it, although there's other schedules where you alternate between low and high and low and high. And so if you want to learn more about that, you can click on this link. We have to choose the batch size. And the batch size is connected with the learning rate. As we saw, the smaller the batch, the more gradient noise there is, and the smaller the learning rate we need to compensate for that, to smooth out that noise. So these two things should be chosen together. And then finally, we have to decide how many epochs to let this thing run for. And by looking at plots like this, we can often decide the number of epochs. Now, the number of epochs is also connected to the batch size, right? Because, is it? I guess, okay, it is in the sense that if I make my batch size half, then per epoch, I'm going to do twice as many updates, right? So I'm going to do twice as many updates, but with a smaller batch, a noisier update each time. So there is kind of a connection between number of epochs and batch size. Another option we have is we could use L2 regularization on the weights. And this is done actually through the optimizer. So when you instantiate that optimizer and you tell it the learning rate, you can also tell it a certain weight decay, which just puts an L2 norm penalty on the weights in the optimizer itself. So that's how you can do that. And so as you can see, there are a number of things we have to decide, and ideally you would decide them jointly, or maybe you would go through circularly, like you would optimize one, another, and so on, and then you come back and see if you should revisit your choice, and maybe you do that a few times. If you want to make it more automated, and you have enough computing power, you can use a package that tries to optimize all of these, or as many of these as you tell it to. And the most popular package right now for this is Optuna. And so with Optuna, what you do is you tell it which things you want it to optimize, which ranges you want it to look over, and what it will do is it will generate basically random combinations, and it will see how it's working, and maybe if it's not working well, it will give up early, or it will see how each combination worked, and then if it worked well, maybe it will choose something nearby to see if it can make it work better. So it has sort of a sophisticated way of choosing which hyperparameters values to focus on given what it's learned so far. So generally speaking, this is going to be a lot more efficient than a grid search. Grid search is great if you have one or maybe two dimensions, but once you get to more dimensions in a grid search, you can just imagine that there's a lot of parameters. Even in 3 dimensions, there's so many different parameters. Basically, the number of parameters in a grid search increases exponentially with the number of dimensions of what you're tuning. So it becomes inefficient. So that's why Optuna, these smart random searches can do better. Yes?
What's the difference between parameters and hyperparameters?
Oh, I guess in a neural network, we call the parameters like the W and the B. And then the hyperparameters are these things like number of hidden units, activation functions, optimizer, batch size. So they're kind of at a higher level of, does that make sense? Yeah.
We say that parameters are something we are going to learn, and hyperparameters is something we can tune.
Yeah, that's a great way of putting it. Parameters are what we learn, like what the optimizer, they're in our loss. That's what the optimizer works on. Those are the gradients we compute in backpropagation. Those are the parameters. Hyperparameters at a higher level, they're things we have to choose, or we have to run some higher level algorithm that does some other search over them. Something like Optuna. Yes.
So was the demo for the 2-layer neural network? Okay, so
There's two. There's an MNIST 2-layer network, and then there's this other 2-layer network. There's 2 demos.
So where the code is that specified? How would that change? Adding layers, how would that change?
So in this code, so these are again 2 layers, but let's say you wanted to change the number of hidden nodes, you would just change this value and you'd run it again. Or we had, for example, like the optimizer, you want to change the learning rate, you change it here, run it again. So if you want to use Optuna, then you write your code in a slightly different way. You give Optuna the list of the learning rates. You tell it how to interface with all your stuff, and then it will run your stuff and try different learning rates and so on. So Optuna could be useful for the project, but it's the sort of thing where you have to have the resources to run it. You might let it run for a few days to see what it comes up with. It's quicker to try to manually tune things yourself, but it's interesting to see whether you can. I think if you configure this properly and let it run for long enough, it should really find the best or a very good set of parameters. Probably as good or better than you could do yourself. But you have to have the resources to do that. All right. Okay, any other questions on hyperparameters? All right. And so let's come back to a discussion of the loss. So I mentioned before that there's different ways to specify the loss in PyTorch. So one example we saw with binary classification is we can write the binary cross entropy. Like this is the way that we derived it back in Unit 5, and this uses the output scores, or sometimes logits they're called. But you can also put those scores through an output activation to get these numbers between 0 and 1, and then you could write the binary cross entropy like this using those activations. And mathematically, if there's no rounding errors or anything, these should be identical. But they're just two ways of programming it. So you have to make sure that you tell PyTorch, which of these you're using. So for example, if you want to do this one, you want to tell PyTorch to use BCE with logits loss. And then you give it those logits, those scores. On the other hand, if you want to do this, you use BCE loss. So that's what we used in the demos. And that takes these activations as the input. If you give, BCE loss, the Z's as the input, it's not going to work well. It's going to work very poorly. Likewise, if you use BCE with logits and you give it the A's, it's not going to work well. So you have to make sure that you construct your network, consistent with your loss, and you tell your loss the right variables to use. So that's for the binary case. We have something similar in the case of 3 or more classes. So cross entropy loss is the most common one to use, and that's going to take these logits or output scores as the input. You do have an option if you want to put those Z's through a softmax, and let's see. So here I wrote log softmax. Okay, I'll need to check that. In my mind, it would just using the softmax, but perhaps it is log softmax. If you want to compute these output activations, then you would use NLL loss. So again, we have to make sure we're using the right loss for the values coming out of the network. And there's a nice blog post about this if you want to read more about all this stuff. Okay. All right. So I think that's actually it for this unit. Are there any questions? All right. So, went a little bit out of order, so yeah. So we finished everything. All right. Well, the next unit to discuss is going to be convolutional and deep neural networks. So in this case, we're going to have many more than 2 layers. We're going to talk about building our linear layers with a bit more structure so they do convolutions instead of just simple matrix multiplies. And we'll talk about a lot of other things to make these units, these networks work well. But I think given that it's 5 minutes till the end of class, we can just save this for next time. So we'll just end class a little bit early today and get into our next unit next time. All right, any question? Yes?
So in the previous lecture, in the performance and e-alter.
Yeah. This one or
No, I think that's on page 20.
this one?
Yes, so how do we explain that there is a flat stage in the training calculus?
This one?
Yes.
So remember, the accuracy is looking at what happens when you round the values. So it could be that like the values before rounding are getting better, but after rounding, they're no better. So that's part of the explanation, I think. So like the loss is getting better, but somehow we don't see it yet in the accuracy. Once things are good enough that we're kind of, when we're rounding, quantizing those values, then we finally see it. But you can see that still there's a lot of weird stuff that goes on. Like here, the accuracy is not monotonically improving, like it's kind of bouncing around even as the loss is going down a little bit. So it's hard to explain exactly what's happening here. Generally speaking, the loss tends to go down and the accuracy tends to go up, but sometimes in neural networks, after a certain number of epochs, the performance might actually get worse. And so they call it early stopping, where you try to figure out exactly when is the optimal time to stop the algorithm, because maybe letting it run too long is not a good thing. So that's actually, you could say, another hyperparameter. It happens in some problems but not others. So I think in this case, probably if you'd let this run longer, I don't think the accuracy would get much worse. I think it would probably settle out and bounce around a certain value. This is all connected to the fact that this is a non-convex optimization problem that we're solving now because of our nonlinearities in our network. So let's go back to the picture. So if all we had was this, and we had that cross-entropy loss here, then when we optimize these weights and these biases, you can prove that it's a convex optimization problem. And as you minimize the loss, there's no local minimum to fall into. But because of these nonlinearities here, once you optimize these parameters, you find that there are these local minima. And so, there's all kinds of, it's just a much harder optimization problem, and that is part of the reason that explains why the performance can be kind of strange. You can basically be within one local minimum for a while, and then you can jump out and go to a better one, or maybe you can jump out and go to a worse one. That's possible too. So that's part of this non-monotonic behavior.
Thank you.
Sure. All right, any other questions? Okay, all right guys, well, we'll see you on Friday.